as I said, we are almost done, but still I would like to go back to saltwater intrusion because I was not fully happy with the lecture that I gave on Tuesday, and in particular I was not fully happy of the fact that I used different symbols with respect to what it's reported in the web pages. So if you don't mind, I would like to go back to the proof that I proposed to you in order to locate the position of the saltwater wedge. Very briefly, and also I take this opportunity to say that I extended a little bit the web page by adding some more steps to the proof. So if you have a look, I extended it yesterday, so if you have a look now, it's a little bit more extended. But let me, as I said, summarize what I said, and let's refer to a situation where we have this cross shore profile of land and seabed. This is sea level. This one is sea level. And here we have the seabed and here the land. And as I said, let's suppose that we have a saltwater profile that is something like this. Actually, what happens in reality, it's less pronounced, meaning that usually the freshwater table raises more, not so rapidly. Because with a similar situation, it's clear that you don't have any saltwater intrusion. When you have the freshwater table located at a so higher elevation with respect to the sea level, the freshwater flow dominates. In such a situation, what you have, it's clearly, it's a flow of fresh water into the ocean rather than the opposite. And we will have the opportunity to check this in the exercise that I will propose to you shortly. But, you know, in order to be clear, I need to exaggerate the scale a little bit. So what we know is that, what we studied is that there is in the underground a surface which in this cross-section profile appears as a line which separates salt water from fresh water. Here we have salt water and here we have fresh water. It is a line under the assumption of no mixing and under the assumption of static conditions. So if everything is static and we have no mixing, there is a line which in 3D becomes a surface separating salt water from fresh water. And what I said is that it's important for us as engineers to locate the position of this separation line. And in order to locate its position, we have to focus on a fluid particle which is standing on the separation between separation surface line in 2D between salt water and fresh water. And if everything is static, this particle is in equilibrium. And as I said, it is subjected by the pressure of fresh water above it and the pressure of salt water above it. Because the pressure of salt water through the medium, through the soil, comes into the soil and pushes this particle of fluid, which is located in the underground, up or down. So let's compute these pressures of fresh water and salt water. And let's take these symbols. We take, with the symbol we indicate, with the symbol capital H, the height of salt water above the fluid particle. This is capital H. and we call lowercase h the excess of height of fresh water with respect to capital H, with respect to the sea level. Okay. Now we can write the equilibrium condition here, and we can write that gamma S, specific weight of salt water, times H is equal to gamma F, specific weight of fresh water, times H, capital H, plus lowercase h. This is the very simple equilibrium condition. Keep in mind that gamma S is higher than gamma F. So this is why you need a higher elevation, a higher column of fresh water in order to push salt water back, in order to keep equilibrium here, in order to balance pressure of salt water given by the water column capital H. You need a higher column of fresh water. Okay? Now what is my aim? My aim is to locate, to estimate capital H, which is the depth with respect to a reference, which is the sea water level in this case, the depth of the separation line between salt water and fresh water. So what we do is, starting from the shoreline, we move back, our abscissa moves back into the land, and at each abscissa, at each position in the abscissa, in the x-axis that I select, I want to estimate the ordinate, which is the ordinate of this separation line. So I fix my abscissa, and for each abscissa I need to estimate the ordinate of the separation line with respect to a reference level, which I take as the sea level. So what I need is to estimate capital H for each possible position along this direction, which is my abscissa, landward. So my unknown here is capital H. Okay, so let's estimate it. And in order to estimate it, I need to take this product at the right hand side. So I write gamma S times H is equal to gamma F times H plus gamma F times lowercase h. Of course, I need to know what is lowercase h. So at each position that I look for, like here, I need to know the position of the water table. And my unknown is the depth of the saltwater wedge given by capital H. Is it clear? And then we will make an exercise so it will become clear, but still I would like that it's clear already now. Okay, now given that my unknown is capital H, let me write capital H, which multiplies gamma S minus gamma F. This is equal to gamma F lowercase h, and then I can compute uppercase H, capital H, is equal to gamma F divided by gamma S minus gamma F is it correct? Let me see. Yeah, it's correct. This is what comes out. And now let's have a look at this ratio here. Gamma F divided by gamma S minus gamma F. So what are typical values for, I think we already discussed it, but let me, if not, let me give you typical values for gamma F. This is very easy. It's 1000 cubic meters per second. No, sorry, 1000 kilograms. Or let me say, the best thing would be, let me do like this, because okay, let me say 1000 kilograms, but it's kilogram force divided by cubic meters. This is specific weight, so I should use Newton here. What is the reason why I thought a little bit what is the unit that I should use? Because I should use Newton in order to work in the international system. Let me use kilogram force, which is technical system that we use sometimes in Italy, and which makes computation more easier, let's say. But of course, if you want to use Newton here, you have to write 98110 Newton. Okay, you could write this. Doesn't change anything. Okay, now gamma S, specific weight of salt water. This is something that you may not know. It's typically for medium salinity. We take 1024 kilogram force divided by cubic meters. Okay, now what is the result? If we compute this ratio here, it's 1000 divided by 24, which is about 40. So this is the result of this ratio here. It's about 40. It's 41. 41 plus something, but let's say about 40. And therefore, what comes out from here is that capital H is about 40 times lowercase h. This is what I wanted to derive. Which means that if you have an excess of fresh water above sea level, which is 1 meter, then this pushes salt water in depth 40 meters, which is nice because it means that you don't need so much fresh water in order to push salt water back. And keep in mind that if you take lowercase h 0, according to this model, if you take 0 here, which means that the water table, it's at the same level than the sea, capital H is 0, which means that salt water goes inland indefinitely, forever, according to this model, which is something that it's intuitive, it's understandable, because given that fresh water is heavier, it goes into the land. But if you have even a small excess of fresh water, then you can push salt water back. And now the best thing to do is to make an exercise in order to check what happens. The exercise is actually very easy, but I think it is very useful. Okay, at this stage we can turn this on. And let's try to introduce an exercise. I am hiding the figure, but we can build a digital one. Keep in mind that this is the last exercise that we develop together. And again, try to be proactive, okay? Let's try to be proactive altogether. Me too, because of course you are proactive if I am proactive. So let's see. Okay, first let me connect the monitor. please can turn off the light, it would be great. Completely. Thank you. Okay, good. So, this is the figure that is on my website, which is equivalent to the figure that I just hide behind the screen. Okay. And let me now look at the previous page, which is the page of the course. This is an exercise which I prepared yesterday. Assessment of saltwater intrusion into the land. The suggested are called, there are two suggested here, I will correct it, and mean, sorry, let me correct soon. I prepared this exercise yesterday, so I was saying, if you see something wrong, please tell me, and the first things that I saw wrong, I want to change it, so we are okay. Just give me 1 second. Okay, now should be okay. Let me see. Okay, suggested are code and data file. Almost okay. So let's look at this, which is a PDF. And the exercise, which is the last one that we developed together, says that it's very simple. There is, first of all, it is given a cross-shore profile. So you see the cross-shore profile of seabed and land in a coastal area is described by the following coordinates. So these are the first table, very simply, gives the coordinates of the seabed profile and later the land profile. So these are the coordinates of the ground. And then we are given the altitude of the sea level, which is located at y equal to 55, while the freshwater level in the land is described by the following coordinates. I think, and let's have a look at the data file. Okay, so it's not the same. Let's look at this table, okay, and then I will change it, because these are the coordinates that you should consider. The other ones are in a different reference system. So basically you have, if you look at the data file, let me see here. You have x and y, which is equivalent, these are the coordinates of this line, which is the ground line. Okay, and then we have the location of the altitude of the sea level is not 55 but 5.5, it's there. And then these are the coordinates of the freshwater level. And you see that the freshwater level, the coordinates of the freshwater level start from an abscissa which is not 0 because it needs to start from the shoreline. Okay? And then it starts from the sea level. The freshwater level starts from the sea level at the shoreline, which is located at x equal 80. And then it goes up. So first of all, what I propose to you is to upload these coordinates in R and draw a graph of the ground, sea bottom, sea bed, and then the land, And then in this graph, we put the freshwater level and the sea level. This is very simple. And again, let's take these, and then I'm updating the coordinates in the other file. Okay, so let me open our window. Let me see if it's big enough. I prefer to increase the font size. Okay, now we have to download the data file, put it on the desktop or wherever you want. This is the usual procedure for I save the link to my desktop of the data file. Here it is. Good. And then, just 1 second. Okay, and then I need to upload the data, and you should be already able to do it. But let's try to do it together. There is a suggested R code. So I have a look at the R code because I don't want to use different instructions, okay, and different symbols. So let's upload the coordinates of the seabed and the land, the coordinates of the ground, and I call this variable bedland, and I need to scan by giving the full path, the data file, and the data file is called, I don't remember, let me see how it's called. It's called data sort intrusion. Let me reduce for a while the font, otherwise I cannot. Okay. So this is the instruction. I am scanning the file, but be careful, in the file there are headings, so I need to skip how many lines? I need to skip 2 lines, and then I need to give the number of data to upload, because if I upload the whole file, then I also upload the other numbers. I need to give the number of data to upload, which are only the coordinates, and I think they are, let me look at the file, they are 14. I forgot something, yeah. Let me rewrite it. Here there were 2 commas, which is not good. So now I accomplished my mission of uploading 14 numbers, which should be the coordinates. And you can make a check. I think it is fine. We can make an attempt. Now we need to separate the x from the y's. So let me write, bedland is equal to the usual procedure, array bedland, dimension equals C2, 7. Good. And now let me write x bedland is equal to bedland 1, comma, and y bedland is equal to bedland 2, comma. I'm sorry that I needed to reduce because we have a screen here that is small. So using large fonts, it's a bit of a problem. but let me try to enlarge it for a while. Okay, now we are ready to plot it. So we can plot x bedland, y bedland, and we make type equal line, and we can use a line width equal to. So let's see whether we were successful. I think yes. The scale here is a bit stretched. Let me expand it. Okay, this is the profile of the seabed and the bedland. This graph should be, let me see, the scale should be adjusted because it's not very realistic in this way. And let me see if I can adjust it. Okay, now it's more realistic. Actually, these are meters. In the abscissa and ordinate, these are meters, and still you see that the scale of the ordinates is a bit expanded, but that's fine. I mean, in this way, it's because if you compare 8 meters on the ordinates with 8 meters in the abscissa, you see that the ordinates are expanded, but that's fine. We can tolerate it. Now it's realistic enough. Now let me put the sea level here. So in order to put the sea level, what we should do is to put a line, and the line should go we need to give the x and y of this line. So the x is c 0, 80, because the location, the abscissa of the shoreline is 80. And then c 5.5, 5.5. Let's use a line width equal to, and let's put color equal, let's use red. There is something wrong here. Let me try with color. Okay, now should work. Okay, here it is, the sea level. I think it is useful if we continue this line, the sea level line, inland, maybe by using a dashed line, not a continuous one. It is useful to put it inland, to continue the line inland on the right, because we will need to check whether the freshwater level is above the seawater level. So I think it is useful if we add another line here, which starts from 80 and goes up to the last abscissa, which is 140. Again red, I would use a line width of 1, and I would use a dashed line. In order to make a line dashed, we have to use a parameter which is called LTY, which stands for line type, and we have to use LTY equal to. Okay, that's it. Questions? Yeah.
When I try to plot the line, an error appears and says plot new has not been called yet.
Because did you draw the plot a bit before? And so let me go back here. And let's make sure that everything was fine with the plot. First of all, did you get this?
Yes.
And it's displayed.
Yes.
Okay. And the instruction was like this. Okay, let me see the error. Okay, let me see there. Adesso l'ho preso, quindi non so perché prima ho fatto così. Ok. Everyone is okay? There are mysteries in the PC, you know. Okay. Either you declare problems or ask questions, or I move forward. Yeah, problem. What is the problem?
We don't know.
Okay.
That's it.
Okay, so I need to check. Oh, no, it's okay.
Okay.
Okay, that's fine. And the lines. Okay. I think the problem is that double parenthesis here. Try to remove one parenthesis, and I think it goes. Okay, good.
What we call the model before.
That's fine.
It's a comma, so.
Okay, let's use an empirical approach. When everything works, we are happy.
Okay, thank you.
We cannot explain everything of our life, so. Okay, and again, either you declare a problem or ask a question, or I move forward. I move forward, okay? Everybody, are you okay? Because you are looking at me with some, okay, uncertainty. Okay, perfect. Now let's, what is our next problem? We have to draw the fresh water line above it, okay? First of all, we need to upload it. So let's have a look at the data file, okay? And remember that we skipped 2 lines and uploaded 14 numbers. Let's have a look at the data file. The data file is here. Data, I downloaded it, so it's here. So you see what is the reason why we skipped 2 lines, 1 and 2, and then we uploaded the 14 numbers. Now we have to upload these numbers below, which are, how many? They are 10, I think. 1, 2, 3, yeah, 10 numbers. And how many lines do we have to skip? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have to skip 12 lines and upload 10 numbers. Very easy. Let's go back to R. Here. And let's call it fresh water, fresh W. Equal to scan. Again, my path. Okay, skip. Now I have to skip 12 lines and upload 10 numbers. So skip equal 12 lines. I could close here because I don't need to specify that I want 10 numbers because it reads up to the end of the file. So let's close here. Good. Let's have a look at it. Perfect. Now I have to separate again X from Y. So again, fresh W is equal to array fresh W dimension equal C2 5. Good. And now X fresh W is equal to fresh W 1 comma, and again Y fresh W equal to fresh W 2 comma. Let's make a check. Let's have a look at X, which is okay, and now Y, which is okay. Good. Now I am ready to make the